Okay, so our topic for today is about power triangles, and another topic is related to this topic, which is the power factor. A power triangle is a type of triangle that is based off of right angle trigonometry. So a right angle trigonometry function looks like this. This side is called our hypotenuse, and this side is called our opposite, and this side is called the adjacent. And there are three basic types of trigonometric functions, which is commonly known as the SOHCAHTOA. So, Ka, and TOA. So is basically opposite over the hypotenuse. Ka is basically adjacent over our hypotenuse. And TOA is basically opposite over our adjacent. This three basic trigonometric function plays a key role in solving for the power factor. Okay, so we can relate this to our topic. This is what a power triangle is like. This side is called as our apparent power. And this side is known as the reactive power. This side is known as the true power. Okay. Our reactive power is also known as the waste energy, or the energy that is not really used or utilized by our circuit. So we'll write it down here, waste energy. And our true power is the type of energy that we use in order to power our electronic supplies and equipments at home. So this is a usable and good energy. Whilst apparent power is the total summation of these two powers. Sum of reactive and true power. We can write the formula of apparent power as AP is equal to square root of true power squared plus reactive power squared. So this is the formula for the apparent power. Another topic for today is the power factor. So as we have discussed previously, the power triangle is a triangle that is composed of three components, namely the apparent power, reactive power, and the true power. And here's our theta. We also know about the three types of basic trigonometric function, and the second type is the most commonly used, which is the cosine is equal to adjacent over hypotenuse. which in this case of power factor, it is it's going to be this is our right triangle. Wait, I'll just clear it out for you. Right triangle. And here's our apparent power, reactive power, and the true power. And we will look for the power factor, which is PF is equal to TP over AP. So as you can see, the resemblance of the two types of formula, they are similar and they correlate to each other. So here are some formulas that we will be needing in solving for the power factor. Yes, these are the few of the formulas. And now I will give an example. So for example, we have a circuit with the voltage source of 120 volts and 60 hertz. And then there's a resistance of, let's say, 100 ohms, an inductance of about 200 millihenries. Yes. Now we have to calculate for the power factor, which is true power over the apparent power. So first we need to calculate for the inductive reactance. Inductive reactance is this. We have to calculate for inductive reactance, so that will be XL is equal to 2 pi FL. So it will be 2 pi F frequency, so that will be 60 hertz. And L will be our inductance, which is 200 times 10 to the negative 3 millihenries. Now we just have to plug it in our calculator, and then we'll get 398 ohms. So this will be our inductive reactance. Our next step is to calculate for the impedance. A formula for calculating impedance is this: Z is equal to square root of R squared plus quantity of XL minus XC squared. Okay, let's solve for it. Z is equal to square root of R squared plus XL minus XC squared. So R, we have value of resistance, we have 100. So 100 squared plus XL, we have 75.398 ohms. We don't have capacity reactance, so that will be 0 squared. And then we calculate that. Square root of 100 squared plus 75.398 squared. 125.239. 125. I'm sorry. 125.239 ohms. So this will be our impedance. So now that we have our impedance and the capacity reactance, we will now look for the current that flows throughout the whole circuit. So So the formula, usually the formula for the current is I is equal to VR, but in this case it will be I is equal to V over Z, since we're talking about a different type of circuit. So I is equal to V. Our voltage source is 120 volts and our impedance is 125.239 ohms. So this is going to be, if you plug it in a calculator, 120 over 125.39 0.9582, 0.95817 amperes. So this is the current that flows throughout this whole circuit. And now we can calculate for the apparent power. Apparent power, which is volts RMS times the current RMS. So based on our formula here, we have AP is equal to volts RMS times current RMS. So we have voltage is 120 volts times current 0.95817 amperes. Now we have to multiply that 0.95817 times 120. So we have 114.98 watts. So this is our apparent power. So now we'll compute for the true power. Our true power is equal to I squared times R. So Ri is 0.95817 squared times our resistance is 100 ohms. So that will be times 100. So that will be 91.809 watts. That is the value of our true power. And then let's solve for the reactive power. Reactive power is equal to I squared times the inductive reactance. So that will be XL, which is this one over here. So that will be I squared 0.95817 amperes squared times 75.398 ohms. So that will give us the value of 75.398, 69.222 watts. 122 watts. So that is our reactive power. So now that we have all these three values, now we can solve for the power factor. Remember that the power factor is equal to the true power over the apparent power. So we will just write it here. Power factor is equal to TP over AP. So TP, value for TP is 91.809 watts over AP 114.98 watts. So we have 91.809 divided by 114.98. So we have an power factor of about 0.7985. Yes. So here's the thing about power factors. The true power is the power that you utilize in order to power your electronic equipments at home. And the apparent power, this is the power that is not used, also known as the wasted energy, according from our previous discussion. Yes, this is the wasted energy, and this is the good and usable form of energy. Another thing about power factor is the closer that they are, the value of the power factor to 1 is better, because this value of power factor shows the efficiency of the circuit that runs within a area. So the closer that this value gets to 1, the more efficient it is. So last time we talked about the power factor, and he said that the closer the value of the power factor is to 1, the more efficient the circuit is. There is another way to get this value closer to 1, which is by adding a capacitor in the circuit. So I will give an example wherein we will insert a capacitor in series with our resistor and our inductor. So we'll just copy our given here. Our given is voltage source of 120 volts and 120 volts and with a 60 hertz. And then here's our resistance and inductance, and here will be our this is our capacitor. So we have 100 ohms and 200 millihenry. For our capacitor, let's say we have 70 microfarad. Yes. So not much will change. Yeah, not much will change. Our inductive reactance XL will still remain the same. So our XL will still be 75.398 ohms. 75.398 ohms. So this will still be our inductive reactance. And now we will calculate the capacitive reactance, which is the complete opposite of the inductive reactance. So the formula for inductive reactance is this, 2 pi FL, right? But when we talk about capacitive reactance, we have to raise this by -1. So our capacitive reactance will have the formula of 1 over 2 pi FC. This will be our formula. So now we'll have just to plug in the value. So 1 over 2 pi 60 hertz times our capacitance is 70 times 10 micro is 10 raised to negative 6 microfarad. Yes. And let's plug it into our calculator and we'll get 37.894. 37.894 ohms. This will be our capacitive reactance. So now that we have both the inductive and capacitive reactance, now we can now solve for the impedance. Impedance Z is equals to square root of R squared plus XL minus XC squared is equal to square root of 100 squared plus our XL is 75.398 ohms minus 37.894 ohms squared. Okay, let's plug it in. 100 squared plus 75.398 minus 37.894 squared. So we have a value of 106.8 ohms of impedance. Okay, now that we have the impedance, now we can calculate for the power factor. For the power factor, we have TP over AP, which is also our TP is, I know I made a mistake. So in this case, this formula is not applicable, but there is another formula to get the power factor, which is this. You can use either of the two, but in this case it will be much efficient and easier if we use the resistance over the impedance. Okay, so now we will be using PF is equal to resistance over the impedance. So resistance is equal to 100 ohms over our impedance 106.8. So we have to plug it in 100 over 106.8. So that will be 0.90363. This will be our power factor. So as you have noticed, the power factor has increased and it is now closer to 1, which made our previous power factor, which shows that this type of circuit is more efficient than this circuit. And always remember that the closer the value is to 1, the more efficient the circuit is in running different types of electronic devices at your home.